So, for this topic, I want to talk about ionic compounds. Now, what we're going to find in chemistry is that it's not just about the elements. We have to put them together to make things. And we're going to find that there are lots of different ways we can combine elements. There are several different models of bonding between elements, how we bring two or more elements together. The first model, which arguably is the simplest model, is going to be ionic bonding. And we're going to see that the reason why ionic bonding is simple is because we can treat everything as a charged species. And what I mean by that is, let's say we have elemental sodium. Okay. Na is sodium. Sodium is typically a nice shiny metal, but it's chemically very, very reactive. If we bring it into contact with something like chlorine, I'm going to write chlorine right now as what's known as a diatomic species, and we'll justify that later on. A chemical reaction will occur. And in case you're wondering, I'm actually drawing a little bit out of chapter 3 right now of showing how to balance a chemical equation. And that's okay, because we're going to see that to really understand the ionic compounds, we should also start thinking about how these reactions occur. Now, as it turns out, sodium typically forms a cation, a +1 ion. Chlorine, we'll see, forms chloride, which is a -1 species. And just because I kind of started writing the chemical reaction, to balance this, and don't worry about balancing too much right now because we'll get to that chapter a little bit later, to make sure everybody is happy as far as how many atoms of each type. We'll have 2 sodiums here, 2 chlorines here, 2 sodiums, 2 chlorines. Now, as we start chemistry, looking at the periodic table is going to give us a lot of information, but it gives us information, but it doesn't give us the why. What we're going to see is that metals, sodium, typically form cations. They lose electrons and form positively charged species. So this would be a +1 cation. Ion means charged, cation means positive, and chlorine forms chloride, which is a negative ion, or an anion. On the periodic table, and I'll give this to you in more detail in class, what we're going to find is the position of an element on the periodic table can often indicate what charge of species it's going to form. Sodium is in the group 1, the first column of the periodic table, so it tends to form +1. Chlorine is in group 17, and it typically forms -1 species. Now, how do I know that? How can you prove that? Well, you can prove it by doing a chemical reaction. How do I know that or justify that? We'll see that we have to come back to a little bit later in the course. So right now, what we're doing is what's known as empirical science. I'm giving you facts, and we're basically doing some things with it, but we don't understand why. Why does sodium form +1? Why not +7? Why not +42? And we'll have some very good explanations of why that's true, but not right now. So you're more than welcome to skip ahead in the textbook. So what we'll find is, like group 1 metals, and running out of space, hydrogen, lithium, sodium, potassium, and so forth, when they form ionic species, they form cations. So hydrogen becomes hydrogen plus 1, lithium becomes lithium plus 1, sodium plus 1, and potassium plus 1, as would rubidium, cesium, and francium. By the way, I'm formally writing out the plus 1. Sometimes you'll just see plus, means the exact same thing. So for charges, it's better to write plus 1, minus 1, but you'll often see plus and minus without the 1, but it means the same thing. On the other side of the periodic table, group 17, here we have fluorine, chlorine, bromine, iodine. So these elements, and by the way, I'm writing them right now as monoatomic species. What we'll see a little bit later on in class is that's not how they exist in the real world. They actually exist as the diatomic species. But right now I'm going to write the elements the way they're shown on the periodic table. And again, we'll get to the subtle differences of why that's not always how we experience what the element is in the real world. So fluorine becomes fluoride, minus 1. Chloride, bromide, iodide. And we'll talk about this with nomenclature. When a metal goes from sodium to sodium plus 1, or potassium to potassium plus 1, we do not change its name in the compound. But for the non-metal, for the anion species, or anion generating species, fluorine becomes fluoride, I-D-E. Chlorine becomes chloride. And that's so in our nomenclature, we know which is the cation and which is the anion, which is the metal, which is the non-metal. And I've given you guys a handout, or will give you guys a handout on the first day of class, that goes through the rules. And it's also part of your reading in the textbook as far as the nomenclature. But in this case, I was more focused, or wanted to be more focused on just the concept of charge separation. But it goes hand in hand with nomenclature. And this part of balancing the equation, again, I'm getting a little ahead of myself of showing that, but hopefully by the time you watch this video, you'll already be approaching chapter 3 in the reading, and that'll make more sense. We'll have an entire section on balancing equations and so forth. So again, you'll definitely want to start getting familiar with the periodic table, the groups, which groups form what charge, and so forth. And again, I'll have that in the handout and maybe make another video a little bit later on.